Swayam Prabha. Digital India. Educated India.
Okay, we begin a new topic today on molecular dynamics. So what we have discussed so far is that for a given system, first step to do is the modeling part. So first we have to find out what is the system that we want to model, whether it is an atomistic system or a molecular system. And then if it is an atomic system, we have to identify what kind of force field to be used to represent the atomistic system, which could be a hard sphere model, or it could be a square well model, etc. In the case of a molecular system, we know that we have to think about site-site interactions, and then we also have to talk about the potential energy due to this angles, bond lengths, and torsional potentials, etc. So this is the first step to do MD simulations. Identify the system and then choose a particular model to represent in the simulations. And the second thing we talked about is statistical mechanics, or the principles of statistical mechanics, where we said that for a system of n particle, and if you're able to generate trajectories, that is the position and the velocities as a function of time. So using these microscopic variables, how to so we take these microscopic variables and then process them to get some ensemble averages of thermodynamic quantities. Sometimes we calculated thermodynamic response functions using fluctuations. And time correlation functions, so that transport properties can be calculated. So so these are the things that we have discussed so far, and the fact that we are able to do or apply a StatMech to measure properties in MD simulation stems from the fact that we are able to generate these trajectories of a n particle interacting system. So now the next point we want to discuss is how do we generate these trajectories? In other words, how do we follow the dynamical evolution of the system with all this modeling part? So that is the context that we want to discuss in today's class. So this basically means that we need to talk about what is known as these equations of motions. So this equations of motion is a very important subject, which allows us to generate trajectories once we have finalized the model. So once we are able to use these equations to generate trajectories, then we can apply statistical mechanics to measure properties in MD simulations. So we will talk about certain types of equation of motion, and in subsequent lectures we will see how to apply finite difference methods to numerically track the system. So to start with, we will first discuss what is known as this Hamiltonian principle. This is the fundamental principle that allows us to derive equations of motion. It's called Hamiltonian principle. So it says that the motion of a system from say time t1 to another time t2 is such that the integral or the line integral defined as I is equal to between time t1 to t2 L dt has the minimum value, where this function L here is defined as kinetic energy minus the potential energy. So, what this basically means is that if you have a trajectory of a system from time t1 to t2, the system will always take a path such that the function L, the Lagrangian, which is defined as k minus v, the kinetic energy minus potential energy, the time integral of this function should be always minimum. So, that is the Hamiltonian principle. From this, we can derive the equation of motion, that is what is the path by which a particle will take a particular path to move from time t1 to t2. So, now in going forward, what we can do is we are basically looking for an n particle interacting system. That is what we want to n particle interacting system is what we want to find equation of motion for. But to make the symbols easy, so what we can do is we can think about a simple system, derive equation of motion for such a simple system, and then we can generalize this for n particle system. The simple system I want to consider is a one particle system in a one dimensional problem, one particle in a 1D in one dimensions. So, we will try to illustrate the principles of Hamiltonian and equation of motion using a single particle in one dimension, that is n is equal to 1 and the dimensionality is also 1. Whereas, once we know this, we can generalize this to n particle system in a 3D system, in a 3-dimensional system. So, first of all, in this case of one dimensional and one particle system, this Lagrangian here L that we have defined here can be written as a function of the position x and its time derivative x dot. I use x because I have only one dimension, so its position can be described by one single coordinate, which is x, and its velocity can be written as the time derivative of the position, which is x dot. So, now when we apply this Hamiltonian principle for a function Lagrangian written as a function of position and the velocity or the time derivative of the position, then it can be shown that the Lagrangian equation of motion can be written as the following. So, this is called the Lagrangian equation of motion. And this is applicable for a single particle in one dimension. And the way we derive this particular equation is by applying this Hamiltonian principle and then ensuring that this integral I has a minimum value along the actual path. Okay, so we apply a principle variational calculus to get these particular equations. So, now if you look at this equation, this looks pretty unfamiliar to you, but then if I take a particular form of Lagrangian for a one dimensional single particle system, then you will see that this equation becomes very familiar to you. To do that, let us take, so we will take a functional form for L as half m x dot square. This is the kinetic energy for the system that we have considered, and then let us say there is a potential energy which depends only on x. Okay. So, this is the kinetic energy part and this is the potential energy part. So, now we would like to see, if I take this particular form of Lagrangian, how the Lagrangian equation of motion turns into. So, and then the Lagrangian equation of motion is this. let's first find, for a given functional form that we have taken, let us find what is dou L by dou x and then what is dou L by dou x dot. So, dou L by dou x dot, you have to do this. So, you get 1 by 2 m 2 times x dot, and this function will not contribute this because this v is only a function of x, not x dot. So, you get dou L by dou x dot as simply m times x dot. And the second thing is dou L by dou x. So, here only this derivative will contribute. So, we have dou v by dou x, and this is basically the spatial derivative of the potential energy with a negative sign, and that is something we call it as a force. Okay. So, the force is given as the negative derivative of potential energy with respect to the spatial coordinate x. So, now let us substitute these partial derivatives in here. So, we get d by dt of m x dot minus f. Okay. And then we take m out, then we write x double dot. The dot here means it's a time derivative. So, we are doing one more time derivative. So, it becomes x double dot minus f is equal to 0, or, and this something is familiar to you. This is basically the Newton's second law, which relates mass times the acceleration to the force, and this is basically a second order ODE, and to solve this you need two initial conditions, namely x at time t is equal to 0 and x dot at time t is equal to 0. So, once we have these initial conditions of position and velocity, you will be able to solve this equation. So, what we have shown here is by taking Hamiltonian principle as a starting point, we showed how the Lagrangian equation of motion is derived, and in particular we have used this for one particle one dimensional system, where we can use x and x dot as the coordinates and the time derivative of the coordinate. And then when you take a simple Lagrangian functional form for the kinetic part and the potential part, and you can show that this Lagrangian equation of motion basically gives you the Newton's second law as you would expect. Okay. So, this is one way of solving the MD trajectories. So, what we have done for single particle, now you can do for n particle system also. That means I am going to put an I here, and then instead of x I will have the full coordinates in all 3 dimensions, and similarly this f will become a vector having all 3 components of forces. Okay. So, this is one way of solving the trajectory for n particle system. So, there is another equation of motion which we call as Hamiltonian equation of motion. Again, to show this Hamiltonian equation of motion, we still again take the same example of a single particle in one dimensional problem, and then show the relationship between Hamiltonian equation of motion and Lagrangian equation of motion. So, first the Lagrangian equation of motion, we said this Lagrangian is a function of position x and x dot. Okay. Now, we think of a Hamiltonian as h, which is a function of x and p, where p is the momentum, and we also define that this p here is nothing but the partial derivative of a Lagrangian with respect to x dot. Okay. So, this is a choice that we have made, that the Hamiltonian of the system can be represented by the position of the particle as well as the momentum of the particle, and then we also say that the derivative of L with respect to x dot is nothing but the variable p here. Okay. This is the definition. So, this may look little bit unfamiliar, but again if you take a Lagrangian form like we took before, that is half m x dot square minus v of x, and then if you see the partial derivative of L with respect to x dot, you get mx dot, and this is nothing but p. So that's what we have defined the momentum as the partial derivative of Lagrangian with respect to x dot. Okay. So now what we have to do is, we have one function L as a function of x and x dot. We have another function Hamiltonian, which is a function of x and momentum. However, this momentum variable p here is dependent on the partial derivative of Lagrangian with respect to x dot. And so when you have two such functions related by this, you can apply Legendre transformations to relate the Hamiltonian and the Lagrangian. So the Legendre transformation gives us that H is x dot p minus L. Okay, so this is the Legendre transformation of Lagrangian with respect to Hamiltonian. And we actually use this kind of Legendre transformation also in thermodynamics. If you recall that we define H is equal to U plus PV, or Helmholtz free energy A as U minus Ts, etc. Okay. So so in this case H is a function of S and P, whereas U as a function of S and V, and A here is a function of V and T, and this is a function of V and S. So whenever you have one common variable and the other variable is related by partial differential of the function, then you can always apply Legendre transformation, which we do it in thermodynamics. The same way we are doing it in classical mechanics also, because that Lagrangian and Hamiltonian, they both share one variable as the same, which is a coordinate. The other variable x dot and p are defined by this particular relationship. Okay, so this allows us to use Legendre transformation to define Hamiltonian. All right, so now what we will do is, we will try to take this particular definition and then use Hamiltonian's principle and then Lagrangian equation of motion, and then use those formulations to find what is the Hamiltonian equation of motion. Okay, so let us first write this H is x dot p minus L, and then we have that let's write the differential form of dl, which can be written as dou L by dou x dx plus dou L dou x dot dx dot. I am able to write this because I know that function L is a function of x comma x dot. So any small change in L, which can be written as dl, is a sum of partial derivative of L with respect to two variables, x and x dot, and then multiplied by these difference variable dx and dx dot. So now we already have wrote that in the previous page, we have defined that dou L by dou x dot is p. So we're going to use that here. So this dou L by dou x dot is already defined as the momentum. Okay, this we know, and we want to find what is dou L by dou x is. So to find this out, we go to the Lagrangian equation of motion, which is this. Okay, and then let's substitute for dou L by dou x dot as p here. So you get dp by dt minus dou L by dou x is equal to 0, or in other words, dou L by dou x is nothing but p dot. So we have got the partial derivative of L with respect to x dot as momentum, and the partial derivative of L with respect to x is the derivative of momentum. Okay, so let us substitute this in this equation. So we get the total derivative dl can be written as p dot dx plus p dx dot. So this is basically the total derivative of the Lagrangian in terms of two variables. So you can clearly see that the dl can be varied, the Lagrangian can be varied by changing x and x dot, and these are the coefficients of those changes. So now let's come to this Hamiltonian. I write a differential form for dH, and then we will use this change in dl in this equation and try to get Hamiltonian equation of motion. All right. So, so since we have written from a Legendre transformation, we have written Hamiltonian as x dot p minus L. We also know that Hamiltonian is a function of x and p. So, like we have written here, we should be also able to write dH is equal to dou h by dou x dx plus dou h by dou p dp. Okay. So, this is one equation. Now, we also have the another expression for h from here, and let us write the differential of that. So, this is going to give you d of x dot p minus dl. So, we will use chain rule here. We write x dot times dp plus p times dx dot minus dl, and the dl for dl we will use this equation. So, you can see this these two terms cancel, and then we are left with simply x dot dp minus p dot dx. This is the derivative of Hamiltonian. So, you can see this derivative of this Hamiltonian can be changed by differential amount of change in the momentum and the position x. So, the same way that we have derived for dl, we have an expression for dh also. And now we have another equation that tells about the derivative of dh as well. So, now let us compare 1 and 2. So, when you compare 1 and 2 component wise, you can see the coefficient of dx here and the coefficient of dx should be the same. Similarly, the coefficient of dp here and the coefficient of dp should be the same. And when you compare, you can show that so comparing coefficient of dx, you get p dot is equal to dou h minus dou h by dou x. And similarly, when you compare the coefficient of p dp, that is this term and this term, you can show x dot is equal to dou h by dou p. So, this becomes the two set of Hamiltonian equation of motion. So, these are called Hamiltonian equations of motion. And if you see, this is basically two first order ODEs. So, to compare, you can see that when we talked about Lagrangian formulation, where we defined Lagrangian as the kinetic energy minus potential energy, we showed that it boils down to Newton's law of motion, which is a second order ODE. Whereas, when you apply a new functional form for the Hamiltonian, and then when you apply this Hamiltonian principle, we basically get two first order ODEs, one that talks about the rate of change of the momentum, the other one that talks about rate of change of the position. So, we consider these two as set of Hamiltonian equation of motion. So, now what is the physical meaning of the Hamiltonian here? So, we have defined the Hamiltonian using Legendre transformation as x dot p minus L, and to see the physical meaning, let us take this some example of example formulation for Lagrangian as kinetic energy minus potential energy, and let us substitute this here. So, you get x dot and this we also know that m times x dot is equal to p. Okay, so this is the definition of momentum. So, let us use that here. So you get p square by m minus 1 by 2 p square by m minus v of x, and this gives half m p square minus v of x. Okay, actually there should be a plus here because, yeah, yes, and this is nothing but the total energy. So H is equal to E. I mean, if you recollect, we have already defined Hamiltonian as the sum of kinetic energy plus potential energy. Yeah, K plus V, yeah, and that's what we have shown here for this kind of example as well. Hamiltonian of the system is nothing but the sum of the kinetic energy plus potential energy, whereas Lagrangian was the difference between the kinetic energy and the potential energy. So when you have, you have to start with certain form of energies or some form of kinetic energy and potential energy through which we can derive set of equation of motions. For the Lagrangian definition of this kind, we have defined what is the equation of motion. Similarly, for the Hamiltonian defined as this, which is nothing but the total energy of the system, we have defined two equation of motions that was shown here. So we have x dot is dou h by dou p, and p dot as minus dou h by dou x. So now that we have a functional form for the Hamiltonian, we can find what is this partial derivatives are, and then we can write what is the equation of motion for one particle one dimensional system. So for the x dot, dou h by dou p from this equation will give you p by m, and for this p dot is minus dou h by dou x. So that is going to be minus dou v by dou x, which is nothing but the force. So this becomes the set of Hamiltonian equation for this particular problem of our choice of the Hamiltonian and the potential energies. So we are basically able to define Hamiltonian and the corresponding two first order ODEs. By solving these two ODEs, you can actually find the trajectories of the system by generating time x and p. Okay, as a function of time, you can get a sequence of position and momenta, and that's a trajectory that you generate in your MD simulations by numerically solving them, and that's what we use in statistical mechanics to find average thermodynamic properties, response functions, and time correlation functions. So what we have demonstrated here is the two different kinds of equation of motion. One is this Lagrangian, which boils down to Newton's law of motion. The other one is Hamiltonian, and the Hamiltonian form is slightly different from Lagrangian because the independent variable that you choose in Hamiltonian are the position and momenta, whereas in the case of Lagrangian, it's just only the coordinates and the velocities or the time derivative of the positions. So now, having done these things for one dimensional system and the single particle system, that is, we are able to write coordinates or positions as x, and the time derivative of x as x dot, and the momentum as simply p. Okay, everything was now dealt with as a scalar variable. But then when you go to n particle system with three-dimensional system, then all this the coordinates and the velocities, the momenta, they all become vector variables of n particle system. So now let us generalize this for an n particle system, having done this for a one particle system. So for n particle system, so the equation of motion, the Lagrangian form, can be written as d by dt dou L by dou q dot I alpha minus dou L by dou q I alpha is equal to 0. So what is this I here and alpha here? So I goes from 1 to n for n particle system, and this alpha here goes to x, y and z components of the position as well as momenta, and the q here is a generalized coordinate. And the q dot here is the time derivative of q. So then, so what we have just done is generalizing this Lagrangian equation of motion that we saw for one particle one dimensional system to n particle three dimensional system, and that's what these suffixes here mean. And where this L here is the Lagrangian now is written as sum of the following terms. So for the n particle system, Lagrangian can be written as the kinetic energy, sorry, this is minus the potential energy. So in the kinetic energy, we have sum over all particles I is equal to 1 to n, and all the components of alpha from x, y, z, and then we use m times, that's half m r I alpha square. So r I alpha is basically the ith component's x component of the velocity. Okay, and it's summed over all these combinations, and then for the potential energy we sum over the pairs I and j. Here we think of potential energy as a potential energy is a sum of pair interactions, which depends only on the scalar variable Rij, which is the separation distance between two particles I and j, and it's summed over all the pairs without repeating the counts. And so when you use this particular formulation of Lagrangian, and when you use this equation of motion, then you can actually show that the equation of motion is going to be mi times Ri vector double dot is equal to Fi. So now we are writing everything in a vectorial form. For each particle I, there is a equation of motion, mass times the acceleration or the time derivative, the second derivative of the position should be equal to the force, and this force F here is a vector, is given as the negative gradient of the potential energy V. So, so now if you ask how many such questions, how many such equations are there, so we basically have 3n number of second order ODEs. Because I goes from 1 to n, and then for each acceleration there are 3 components, that's why there are 3 n number of degrees of freedom, and you have second order equation of this kind. So now let's look at for the Hamiltonian formulation for n particle system. So we write h as a function of P and Q, and that is equal to and then if you apply the equation of motion, that is Q I alpha dot is given as the partial derivative of h with respect to dou p I alpha, p dot I alpha is negative of dou h by dou q I alpha. So these are the set of Hamiltonian equation of motion for an n particle system. And so yeah, so basically in our MD simulations, all we need to do is write the Hamiltonian formulations and then use the set of equation of motions, and then numerically solve them to generate trajectories. Okay, so numerically solve to generate MD trajectories. All right. There's one last property I want to talk about the Hamiltonian equation of motion. So again, for this particular exercise, we will take, again going back to the one-dimensional problem, and P dot is minus dou H by dou X. So now you might ask, what is the time derivative of Hamiltonian? That is, what is dH by dt? And we can write this as dou H by dou X dx by dt plus dou H by dou P, it's dP by dt. And so what is dou H by dou X? From the equation of motion, we can write this as minus P dot, and this dx by dt is nothing but x dot. That is the time derivative of x. And this dou H by dou P is given by x dot here, and this dP by dt is P dot. So that is the time derivative of H along the equation of motion is equal to 0, and we already noted that H is nothing but the total energy of the system, E total, and it says that along the equation of motion of Hamiltonian, the total energy is conserved. So that means if I generate trajectories using this equation of motion, it ensures the total energy of the system remains constant. And this is important because when we talked about NVE ensemble, we said that trajectories should visit all the microstates of energy E. So now we are able to show that if I solve the classical n particle system using Hamiltonian equation of motion, along the trajectories the energy remains constant. That means the trajectory that we generate in the constant energy ensemble basically samples all these microstates of common or the same energy. And so whatever the condition that we imposed on sampling of NVE ensemble through trajectories is actually mapped on by this particular equation of motion. So solving this equation of motion ensures the energy remains constant throughout the trajectory.